the empirical rule, and say, well, we already did that. So we know that we have, I'll call it just a by hand way of doing it. You know, we have a mechanical, a procedural way of getting the job done. But even with calculator shortcuts, we know that it's pretty lengthy. Right? We wrote the program to try to take something that's lengthy into something and make it something less lengthy. Right? But there's still the whole counting part of the process, and it could get messy. So that first process is all that stuff that we worked with. The second process is what I teased, I think, 2 classes ago, using the normal probability plot. Right? The interpretation of this, the plot, once we create it, is the key to everything. And a little statement here. The more linear the points in the plot, the more normal the original data. It's going to be pretty weird, because when you think about something being a normal bell-shaped curve, you would not necessarily think that we'd be looking for the graph of a line to prove that. Right? But that's exactly what we're looking for. Right? So what I figured we would do is go through one case by hand, because this, you know, it's one of those topics where it's like, it's just too good to be true. It falls in the category of hocus pocus, black magic, all that good stuff. And, you know, you could get the answer on the calculator, and that's wonderful. I mean, and for some of us, a lot of us, maybe all of us, I don't know. Maybe I'm just not reading the room. I just want to move this over. That is going to annoy me. All right, let me try it this other way. It looks like, okay, I'm gonna lose my mind here in mere moments. All right, good enough. But it's supposed to be a little bit more seamless than that. I could be also thinking of my Mac. Yeah, it's one of those things, like, you'll get it right, you'll follow the steps, but you'll never truly understand why it works the way it does, and that could be very frustrating. Or not, but I think it would be frustrating. All right, so we have a set of data here. We're asked to determine if that data would be considered normally distributed. All right. So we could do it a couple of different ways. We could use the empirical rule. We could sketch a graph and see, well, does it look roughly bell-shaped? That's not proving anything, but it can't be normal unless it's symmetrical in some capacity, and symmetrical in such a way that the bulk of the data is in the middle and it tails off in the extremes. Right? So that's a way of getting a start on the process. And in fact, we're generally rooting for failure when it comes to this kind of question, because if you graph a distribution and it's clearly skewed in one direction or another, then you know that it's not going to be a normal distribution. So you could dismiss it immediately. So that would be a good thing. The best way, I think, to handle that would be, first step, create a box plot. Because if you see a tail on one side that's significantly longer than the other, then you know to stop. I'm not even going to look for a normal distribution, because it's not symmetrical. So it could not be even approximately a normal distribution. But assuming that it passes that step in the process, that visual step of saying the two tails of my box plot are equivalent in length, roughly equivalent in length, they don't have to be perfectly equivalent, then I'd have to start the process of proving normality, right? And you'd end up using a process like this. So what we're going to do is find z-scores for each one of these values, all right? So let me do this. First off, let's get the data in, stat edit. Just a reminder, when you're clearing out your data from a list, you go right up to the column heading, do not hit delete, hit clear, and then hit enter. And it'll wipe out all the contents of that list. All right. If you hit delete, it's going to wipe out the list itself. All right. Not impossible to recover from. but not a road you want to go down. I mean, during class it's fine, but on a test, that's a pretty panicky sort of feeling that students have. I broke my calculator. Like, no, you didn't. All right, so a couple of ways to handle it. Well, first, we might as well do the box plot thing just to see. All right, so I'll do that. So second, y equals, my data is in plot 1. So you do have an indicator of what the function is and what that function is representing. Just in this screen, you can see plot 1 is turned on, for me anyway. It says that it's referencing L1 with frequency values of 1 for a box plot. So my plot 1 is ready to rock and roll, but if yours isn't, you would hit enter on it, hit enter on the word on, down arrow, go over to that box plot. There is a modified box plot that we're going to talk about next class, but that's for next class. Just make sure that it says X list L1 and frequency list. If you didn't put in a frequency table, then it stays at 1. If you did, then it changes to L2. All right. Make sure your alpha lock isn't on. For some of you who have that little issue, when you get down into this area, sometimes it automatically turns alpha on. If that's the case, you can either quit out second mode or just hit the alpha key again to turn it off before hitting zoom 9. All right, so we're looking at a roughly symmetric looking distribution. Undo. All right, so this is, I mean, it seems like it's more than roughly symmetric. It looks beautifully symmetric.
I think it's given to the left.
That, I mean, that is ever so slightly. Yeah. So here's the deal. If it becomes a matter of an eye test, then it's not a skew. All right. The length of one tail has to be significantly and noticeably longer than the other tail. If it's ever so slightly longer, we don't call that a skew. All right. We could say that in fact it's almost symmetrical. You're going the other way. Like the benchmark is symmetry. We're going to look at that and say it's not quite symmetrical, but we're not going to say that it's far enough away from symmetrical to be skewed. All right. So what I mean by the eye test, you're looking at it and saying, well, let me squint, look at it from this angle, that angle. Yeah, I guess the left one looks a little longer than the other. Let me get a ruler on that bad boy. If you got to do that, then you're not saying skew. All right. It has to be clearly and noticeably longer on one side. All right. So, how do you zoom in? You hit zoom, and then zoom in. Yeah. It's one of the few things that's intuitive about the calculator. But almost everything else is not. So.
Because it is just so clearly intuitive, no one thinks about it. Everything else is complicated.
Yeah, like
simple.
There's no way it could be that easy. Yeah, exactly. So we get into the process of determining the z-scores. All right, so I'll just read the process here. It's pretty convoluted, but it's worth getting into just this one time. You must first determine the rank, the percentile rank specifically, for each score. We do this by subtracting 0.5 from the rank of each entry and dividing the result by the total number of values in the data set. The smallest observation is 24.9. It is the first of 9 scores, so the percentile associated with it would be 1 minus 0.5. So we're taking its rank. We'll highlight that. Its position, it's the smallest value in the set, so it's the first position. We're subtracting 0.5 from that and dividing it by the total number of values in the set. And what that does is it gives us a percentile value. All right. So a percentile is generally considered to be the percent of values that are below a certain score in a data set. The problem is you can't really say that there's just nothing below that position 1. Right? We don't really know that. So we give ourselves a little bit of wiggle room. So we go in terms of half units. All right? So what we do is we just reduce each position by half a unit and then take that number, divide it by 9, and that gives you the percent of values that would be considered to be below that. It's a correction factor. All right? There's other ways to find percentiles, but this actually ends up being the tidiest way of doing it. All right, so in the case of the second one, what we would do is figure out what, so again, we have the position 1 minus 0.5. So we're doing, oh, that's weird. Little typo here. I mean, I guess it amounts to the same thing, but that should be 1 minus 0.5. So the next one should be 2 minus 0.5. With my lovely pen here. It should be 2 minus. This was a typo here. It's this calculation. All right, we're subtracting 0.5 from each, the rank of each entry. So the position rank. So divided by 9 times 100 equals, so 1.5, 2 minus 0.5, divided by 9 is that times 100. Is going to give you about 16%-ish. Right? My handwriting is so brutal that it's not going to fit. So I just gotta, let me just move this over. No, I can't even do it. Let me just do it off on the side. So that's about 16.67, 667%. All right. Now,
There was 2 values on there with the exact same number. Like let's say there was 233.0. Would we still categorize it as 4, 4, or would it be 4, 5? Would we have to do it by right?
it would be 4, 4, then 6. Yeah, so like the typical ranking, like if you were running a race, you know.
We just skip 5. We wouldn't lose the next value as 5.
Correct. Yeah, so like in a race, if you had 2 third-place finishers, they're occupying the 3rd and 4th place, but you're calling them both 3rd place. So then the next one would be the 5th place. All right. So yeah, that's a good question. So this part, in my attempt to avoid hocus pocus and black magic, this part is going to seem like just that, but it kind of has to happen. Otherwise, we wouldn't be able to do statistics, right? So what's happening here is you're looking at what would be a normal distribution, and that normal distribution is going to account for about 16, 17% of the area to the left of a certain z-score. All right, and we know z-scores represent the standard deviations, the number of standard deviations away from the mean. All right, so what I'm going to do here is I'm going to identify the 50% mark. So this is about 50%. I mean, it should be 50%, but the way I drew it, it just doesn't look that way. If I were to collect data, accumulate data as I work my way from the left to the right, I start at 0%, I've collected nothing. Then when I get to the halfway point, I've collected half of the data. And then when I get all the way to the end, I will have collected all of the data. So those are some pretty significant benchmarks. When we talk about probability in the next unit, it'll become even more obvious. All right, so these are my reasonable estimates of 0% and 100%. Not precisely, because these graphs go on forever. 16%, I don't know where that's going to be, but I'm just going to ballpark it as right here. What that's going to give me.
Question. So you got 16% for position 2, is what you're saying?
Yeah, I just wiped it out of this cell here because I couldn't fit it. But it's for this entry.
So the
All right. So now what we need to do is figure out the z-score that goes along with that value. All right. So that's the black magic part. But this is about, I'll call it 17%. Just so I don't have to put crazy decimals in there. What we're about to do is going to give us the z-score that corresponds to that number, that percentage value. All right. The hocus pocus step that I was referring to. So we're going to use the inverse norm function. I forgot the n. All right, what that does is it returns a z-score for a given percentile. All right, it returns a z-score for a given percentile. In INV norm, it's me rewriting this command. It's a command in the calculator. That new pen can't come soon enough. So to get there, we're going to hit second vars. And it's going to be option 3.
what does the green say?
17%, yeah. Approximately. And so in these calculators, it depends on which model you have. If you have the older model TI-84s or TI-83, when you select this option, what comes up on your home screen would just be INV norm. See, this is just evidence that my handwriting is not terrible. Like, it's not good, but it's not that. Like, it's not working with me. You know, so whatever. Anyway, you'll see, when I get my new pen, everything's gonna work. I'll show you beautiful penmanship, magic. It's gonna be great. Anyway, so this is what would come up on your home screen if you have one of the older calculators. All you're gonna do is type in the percentage value. Alright? So the thing is, like, here's a percent value. but the calculator only accepts the decimal form of that. So this is where we get into the issue of marrying, you know, theoretical statistics and what the calculator wants. All right, so here we would put the percent value, but in decimal form. So what you're looking at really is this computation, but you never really had to multiply by the 100, but in order to conceptualize it as a percent, you really kind of need to. All right, so 1/6, we'll say 167. And that's going to spit back the z-score for you. All right, so for the newer calculators, you'll see mu and sigma are given as 0 and 1. For now, we're going to leave it that way with no explanation. I'm not going to tell you why, because that's a different lesson in and of itself. But we're just going to leave it that way. We're going to go to paste, and we're going to hit enter. And in fact, you see how this brings up this display? We don't have to have the 0 and 1. That 0 and 1 is assumed. And so we get a z-score of 0.966-ish, negative.
Why does mine say left?
Yours says what?
Left.
Because it's fused to the left, right?
After 0 and 1.
Yeah, exactly.
It's
Yeah.
left.
The center, right? The tail.
Say it again.
We would put the tail to the center.
Oh, Christ, there's another update? Yeah, left. Left is what you want, because what it's doing is it's asking you where that percent is on the graph, and it is to the left of the number that we're looking for. Yeah. Yours says what? Norm? Just like the answer as a result? It says that's a new one.
Norm for norm.
Oh, okay, so you're at the point where you're ready to hit enter. It's just, you see that arrow there? It's telling you that it really does says inverse line, but we scroll through it. Now we need enter. You just have to hit enter. Oh, that's fine. Go to go to. 0.167.
So then, if ours says left, right, then the decimal that shows over there, like, that would be irrelevant for us. If it's just telling us that it's going to be to the left.
Well, the thing is, you're telling the calculator where this percentage is on your graph. Is it on the left side, is it on the right side, or
It's
is it in
just a
between?
location.
It's a location of it. So if you said right, the calculator would think that you wanted the 17% to be on the high end, which would be a problem, right? At least for this kind of question. There are some situations where that's going to be useful.
It's asking who the tail is, actually.
Right, exactly. That's what that's referencing, right? And so when we get to inferential statistics, it'll become more clear. But for now, just put it on left and leave it on left. All right, so negative 0.966-ish. All right. Now you could already see how this would be a troublesome kind of proposition. You know, you want to do this every single time? Of course not. But there is a relationship. And so what you would be looking to do here is plot your data in ascending order against the corresponding z-scores, all right, based on the rank of the data values. All right. The good news is these values are never going to change. All right, these z-score values that we come up with, because they're based off of the rank of the data points. All right. Okay, so maybe they'll change slightly, but they're not going to wholesale. It's not going to be like a wholesale change. The only time that there would be a change in value would be if, for example, you had a tie, repeated values. But that's not going to be the case, at least here. So the next calculation would be doing the exact same thing, just replacing the 2 with a 3. So every other step is exactly the same. You're just replacing the 2 with a 3. So I'll run it through. And really, you could even eliminate the step of multiplying by 100. And actually, you could even simplify it further. Because if you really think about what we needed here, we had to compute by taking the rank subtracting from that rank 0.5, dividing that result by the total number of values in a data set, which is 9 in this case. Now, just for the sake of understanding, we multiply that result by 100, but we never really had to do that. So in the next step, after we computed this value, we got some number. We then found the inverse norm of that value, all right? So whatever that number ended up being, that got chucked in here, and that told us the z-score. Let me get rid of that. I meant to make a dash. All right? So really, I mean, if you want to streamline the process, inverse norm, so second var is option 3. Instead of computing the decimal value of the percentile rank separately, why not just do it right in here? You know, so the next number is 3 minus 0.5. So that gives me a 2. Divide that by 9, but don't multiply it by 100. It does that for some reason, I don't know. Then go to paste. It automatically populates in the 0 and 1. So if they're there or not there, it doesn't matter. If you're working with an old school calculator, you don't even need to put them in to begin with. Hit enter, and it'll give you the next entry. So it should be about negative 0.589. You start to learn the magic of the second enter command. Second enter just recalls the previous line. Just go back and change that 3 to a 4. You get the next entry. So negative 0.282. Second enter to call the previous command. You get, for the newer calculators, you hit the up arrow if you want, but I like second enter because it's going to reproduce the thing that you want, the most previous calculation. Then you're changing the 4 into a 5. Solid 0. 0 is a beautiful number, not for the obvious reasons only, but because a z-score of 0 falls smack dab in the middle of the graph. All right, so it looks like the middle entry in my data set also happens to be consistent with the z-score of 0, which is good to know. Because indirectly we just discovered what the mean was. Oh, I hit second enter and I just hit enter again. Making it a 6. So 0.282. Now, based on what I'm seeing here, I have a sneaky suspicion of how things are going to play out. We're going to get the same values, but they're positive counterparts. All right, so we're looking at 0.589. Point 967 instead of 966. 9. But it's pretty close. Hit enter, second enter. And then the last one, last and final, would be the 9. And we're looking at 1.59-ish. 1.59-ish compared to negative 1.59-ish. So we're looking pretty good. Let me get this. So hideous. I'm just going to pop this over here so we can reference it. Oh, jeez, look at that. So to create the graph, and after we do this, I'll show you the real nifty shortcut. And then I guess maybe you'll hate me for making you do all this. But then at least you'll have at a minimum, some appreciation of the work that you won't have to do. I'm kind of big on that because I never. One of my biggest pet peeves is when people complain about the calculator approaches to doing things, and the only reason they're complaining is because they never had to go through what I went through of spending hours having to do this crap by hand with a 4-function calculator. You don't know how good you have it. So I give you a taste of just how bad things could be so that you start to develop an appreciation for someone to not make you have to do it. So anyway, I'm going to plot these values against the corresponding z-scores. All right, so these real values from the data set, these are the values on the x-axis. And these would be on the z-score axis. All right, so I'm going to plot 24.9 as an ordered pair against negative 1.59. So I'm going to estimate 24.9 is like right here. 1.59 in the negative direction is going to put us somewhere in the neighborhood of around right here. So we just go there and we plot a point. Then 28.5 against the negative 0.966. So 26, 27, 28, 29, so 28 and a half, and a smidge shy of negative 1. Roughly about right, yeah. 29.4 against, it's in the negative 0.6 range, that area. So just ballparking it again, it's going to put us about right here. 32.1 against negative 2.82. So 31, 32, somewhere in this neighborhood. And then we're looking about right here. Then it's negative 2.82. So it's actually going to go below the line. About right there. The next one is 0 at 33. Some of the vertical lines got chopped out. I can't figure out how to put them in, but that doesn't mean you can't claim it as a typo. I'll just keep giving typo bonus points every semester. But you see how we lose one around right here and here and here. Like those should be there, but they're not. Just got to eyeball it. 33 is 0, I got that. 33.4 is about 2.82. So we're looking at 0.282 is what I meant to say. 36 and change, and a little bit less than 0.6. So we're looking at about right there. 38 and change, a little shy of 1, so about right there. And then a little bit north of 40 and a little bit shy of 1.6. So we're talking like right there. All right. So that's what we call a normal probability plot. But the interpretation is the key, because like I said, in about a second, I'm going to show you how to do this like that on your calculator. You've got to be able to interpret it. So the normal probability plot is almost linear. You could say almost linear, you could say close to linear. You know, you put a ruler on it, you're going to get a fair few of those points, you're going to miss a few. It's not going to be perfect. So you could say close, I'll say close to linear. So then we would say, therefore, the data is close. These two words should coincide to being normally distributed. All right, normal probability is close to linear. So therefore, the data is close to being normally distributed. If you were to say the normal probability plot is virtually linear, like maybe just 1 point that's off the line, virtually linear, then you would say the data is virtually normally distributed. Those words should coincide with one another. Whatever descriptor you use for a normal probability plot is the descriptor you should use for normality. All right. So we have our data popped into the calculator. We didn't do that for giggles. There was a reason behind it. The data's there. Go to stat plot. Second y equals. Option 1 generally tend to live out of the same plot editor. Plotter, I guess, works too. Make sure it's on. Hit the down arrow. The very last one is supposed to be reminiscent of a normal probability plot. If it is, you have a better imagination than I do, because I don't see it. All right, but it's the last one. It looks like kind of like a step function, if you're familiar with pre-calc concepts. But that's the one you want. That's the normal probability plot. All right. Normal probability plot does not accept frequency distributions, so it would all have to be in a single list of data. Right? But that being said, if you had a frequency distribution, I don't know that you would need any fancy function in order to determine normality, because it's pretty much set up in the frequency table to evaluate just that. Right? So the default settings are exactly what we want. The data axis should be the x-axis, just like we have here. And the data list should be wherever you store the data, which in most cases is L1. All right, so that's good news. It means that once you select this function, you could go right, as long as you don't have your alpha lock on, you can just go right to zoom stat, and it bypasses the need to create the table. That being said, if you needed to create a table out of it, you could. You just hit trace, hit the right arrow, and it's going to give us all those values that we came up with. You know, without doing any of the work. Oh, it's so great, thank you. Oh, you're so welcome, you're so welcome. And also, the real reason why we would do it graphically is it's going to give us a more precise look at the layout of the data points. So, I mean, I ballparked like crazy. And also, I mean, I'm prone to mistakes. It happens. And people, if you're going to make a mistake, odds are it's going to happen on a test. When you're practicing, you practice 100 times. You'll never make a mistake 100 out of the 100 times. You'll never make a mistake a single time. The 101st attempt is the day of a test. All of a sudden, that's where you make the mistake. It's inexplicable, but that's how it is. This saves you from that, and this looks a whole lot more linear than the graph I just created. So this, I would even say, this is virtually linear, because I mean, virtually, damn near means the same thing in my mind. So if you're looking at it and say that's damn near linear, the word you're looking for is virtually, right? Virtually linear. So therefore, the data set would be virtually normally distributed, right? So, I mean, if you want to go a little simpler in the language, that's fine. You can say very, very close. Very, very, just keep adding varies. The closer it is to being a line, the more varies you should throw in there, all right? And then you can't go wrong as long as your descriptor for the normal probability plot matches the descriptor for the normal distribution. Question, please. They're there. All of these heights, like these, along the y-axis, those are the z-scores, and so they correspond. If you were to scroll along on this graph, so when you hit trace and scroll along, the y values that it spits out at you, those are the z-scores.
So the purpose of calculating it is so we know what we're into?
Exactly. Yeah. The underlying theory. So anyway, that's where we're going to leave it for tonight. Brains ready to explode. No, it's not that bad. It's very procedural, but it does take a little bit of practice.